Today I'm going to be talking about reliable systems. It's something I like talking about a lot, something I like building, and the reason for it is simply that it kind of matters. It doesn't matter if you're building software for one person or hundreds of people or millions of people. It tends to be that it matters to somebody. So is there, I guess, most of you work on software for your day job. If you're not there and something breaks today, would there be somebody to be upset or somebody who can't do their job? Yeah? Or everything will go on normally? All writing really good code? So, for me, reliability is this idea of performing consistently well. It has to give us the right answers, it has to keep giving us the right answers every time we ask for them. So if we look at an extreme case like airline travel, kind of reliability is kind of obvious. Do we get safely from here to our destination? But like software, building jet airplanes is actually a really complicated endeavor. It's not actually obvious how all the decisions that you make by themselves make a reliable airplane. So if we were faced with this question right now, one of the things we'd have to decide is how many engines do we want in our plane? If, like most airplanes these days, only need one engine to actually stay up in the air, but we don't have just one engine. Some planes have two, some have three, some have four. If you were designing a plane right now, do you think it would be more reliable to have 2 engines or 4 engines? Can I get a show of hands for 2 engines? Show of hands for 4 engines? Yeah, see, it's interesting. Everyone leaps to having more, thinking that, well, if one fails, then I've got 3 more. The problem is that it has unintended consequences. The interactions between our components matter. If we lose one engine, it could actually cause more damage. So by having 4 engines instead of 2, we've actually increased the chance that we could have a failure. And that failure might matter more than an engine not working. So if the failure damages a wing or damages the cockpit, it could be worse. So there are many situations which 2 engines may be safer than 4. And this is a non-obvious outcome. And we have to think about these non-obvious outcomes when we're building complex systems. So a good way to kind of get a bit of an intuition for this is to kind of understand the probabilities of failure. So this is an exercise I like to go through with people just to kind of get them thinking about what success rates are and what failure of their systems look like. So if we take a service, any service, and we have a look at how likely it is to fail while we're having this talk. This is not a very reliable service. I'm going to say that it has a 10% chance of failing, 1 in 10 chance. So we don't want to get interrupted while we're doing our talk. So let's add some redundancy like the airline. We're going to have 10 services. So if the probability of failure is 1 in 10, when we add 10 services, we actually decrease the chance of a system failure to 0.1 to a 10, right? So that's, if we turn that into availability, we go 1 minus 0.1 to the 10, which gives us 99 point lots of 9s. That's 10 9s availability, better than Google and Amazon. So we're winning at life. However, again, like the airline analogy, the independence of these failures really matter. If one service fails, could it have more dramatic consequences? Will it cause other failures? Basically, we want to ask the question, are these failures really independent of each other? Let's have a look at what the consequences of non-independent failures are. If the probability of failure is 10%, then that means the probability of success is 90%, right? We're going to have 90% chance of it succeeding. So when we add 10, the probability of all of them succeeding is actually 65%. Okay? So if we have a situation, which I'm sure as software developers you've seen, where if one thing breaks, everything breaks, mutually assured destruction, that creates an awkward situation. That means the probability of at least one failure is 65%. Means that by adding 10 services, we've gone from a chance of 10% of failure to chance of 65% of failure just by adding some redundancy to try to get our service a little more reliable. This is not how people think about these problems normally. We think, well, we have 2 of them or we have 3 of them. We're adding redundancy, so we're adding reliability. But it often doesn't work like that. We have to architect and design our software in a way that actually supports failure, supports independence. So this talk, I'm going to go through a whole bunch of different techniques and strategies and look at it from 3 or 4 different angles to look at how I think about independence of software and how that can impact reliability. So one of the takeaways I want everyone to have from thinking about these probabilities is that service redundancy basically means more things are going to fail. The more components you have, whether if you have 10 services, you've got 10 times the chance of seeing a failure. But it does come with benefit, which is that we have an increased opportunity to handle that failure. So when we have 10 services, maybe one breaking doesn't matter. When we have one breaking does. It's the reason why everyone put up their hands for 4 instances instead of 2. But we have to remember that that opportunity is predicated on the independence of services. If services are not independent, we don't get the benefit. So what if we have services of different types, which is probably more common, where we have three different functions in our systems, dependencies on other systems? Again, it's all about independence. If we have a 90% available system, a 98% available system, and a 95% available system, well, we end up with about 83% availability. Things drop really dramatically. If we're somehow to make these systems independent, such that if the blue system when the blue system fails, it doesn't bring the other ones down, we can lift it up to 93%. We really want to think about our independence of services and how that impacts reliability. This is the idea of service architecture. We want to control our interactions between services such that we can increase the reliability and increase the tools at our disposal. So I'm going to go through some examples and hopefully this will start to make sense. One of the things that I often get asked when I'm talking about services and talking about reliability is the idea of like microservices versus monolithic architectures and a whole bunch of different questions. It actually isn't that relevant to the idea of reliability, and that's again not obvious to a lot of people. When we have monoliths, where we have all of our code in one repository, there are no network calls. There are some benefits to that, is that networks are unreliable. Being able to not have network calls might make it easier to write the code and might give us a few less failure cases. But when we split up services, we do have those extra costs. But again, the independence of components inside of our services actually can exist in monoliths just as it can in microservices. So one of the things is that if we took a web app that had some search functionality and had that we could put in its own service, but we didn't, we put it in one big app. Search requires lots of memory, lots of computation. It might be the thing that crashes all the time. If we put that with all the rest of our code, we're actually going to bring all of our code down all of the time. It's kind of this idea of magnification of consequences. So service granularity provides the opportunity to trade the likelihood of a failure against the consequences of failure. So by having lots of little services, more things are going to break. But the consequences of those might be able to be more contained. So if the search service goes down, that might be okay. We might be able to still have our website up. If search breaking means that we don't have a website at all, that could be really bad. So we want to think about these trade-offs when we're writing our code. Basically, the things I'm talking about are all going to be opportunities. They aren't things that you have to do or things that are going to make the difference between it never breaking or always breaking. They're just little opportunities to basically ratchet up the numbers of what a reliable system can be. Okay, so let's look at an example of actually building a system. Although I'm not particularly good at it, I enjoy playing online chess. And I find that thinking about online chess as a bunch of different independent services is a really good example for thinking about how to design a system. So that's what I'm going to use as an example as we walk through today. It's not too big, so hopefully it's not too hard to follow. If it is, you can throw things at me. It's okay. So, it's an online game played between 2 people. There are a bunch of rules. So one of the first functionalities that I think about is a pairing service. I want to be able to play against other players. So 2 people go to the site. I need to be able to find a match between those 2 people, organize a game for them so they can go and play. want to actually play the game. So follow the rules, communicate the moves, tell them who won. I want to be able to look at my history. It's great to learn from mistakes. Go and have a look at your past games. So I want to be able to store the history of all of my games. I want to be able to analyze games. Computers are really good at chess. So I want to be able to go and have a computer look at my game and tell me where I made a mistake, where it went well, where it didn't. And I want to be able to play against computers. Playing against computers might make me a better player, or it might just make me lose a lot more. It's all good. So, if we're going to build this as a monolithic service as one big thing, I don't want to argue too much about the idea of having a monolith versus having microservices, but this is just to look at it from a reliability perspective. So this is definitely one approach. So one of the key benefits of having a monolithic approach is that there's no risk of failure due to the interactions between services. So all of those functions are just going to be implemented, and I don't have to worry about how the pairing service talks to the playing service, or how I get the results of the game to the history service. I don't have to worry about those network communications. So that's definitely a benefit. One of the problems, though, is, again, what I mentioned earlier, which is this increased consequences of failure. If one of the services breaks, then everything goes down. And I'll talk a little bit more about that when I get to the service and design. And one of the big downfalls is that it removes any independence of operational control. So basically, you're hostage to your worst features. So if there's something that requires lots of memory or lots of CPU, then I have to scale all of my components together. And that becomes a little bit problematic. It's not the end of the world, but something I have to deal with. So if we wanted to go with a more service-based approach, where we have a number of smaller, finer-grained services for each of those functions that I talked about, one of the most common mistakes I see when talking to people about this is that they go, well, where are all the nouns in my system? What are all the things that I have to know about? And so in the chess game, they would talk about having a game service that maintained game state and a player service that talked about representing a player, thinking about it like objects in an object-oriented system. This has a bunch of problems. If you flush out this system, you'll end up with, well, a playing service, and the playing service has to talk to the game service, and the player service, and the history service has to talk to the game service. And there's a lot of communication overhead and a lot of complexity. The game service might have some state that looks something like this, where it knows about a game, what state it's in, is it waiting for a pair, or is it finished, or is it in play, who the two players are, references to the player service. It has to worry about other states. But if we actually look at the services, the states that the game service is actually storing are all about the other services. It's, well, I have a game that's in the play state, or a game that's currently in the history state. And that game service has to know about all games over all time. So it's going to get loaded. We're going to send lots of network requests to it. It's going to get pretty bad. And what happens when it does go bad? If the game service goes down, getting chopped off a little bit. If the game service does go down, what actually happens? Basically, everything's going to fail. Basically, we've created all of the downsides of the monolithic approach with lots of network calls. So, breaking things into services can make things a lot worse if we're not careful about maintaining our independence. So, what's a different way to design the services such that we don't have this coupling and we can maintain independence? One of the nice techniques to think about is to think about services not storing state about your nouns, but start to think about those things as values that you pass from one service to another. So in our chess case, we could think about the actual game state. So chess has a nice convenient textual notation called PGN, this is the example, where it stores the moves. And so this is a textual representation of the state of a game. So this could be a game that's actually finished, is played, very quick game. We can think about this as a value that we pass from one service to the other. And services don't need to go and ask a game service for the state. They actually get passed it as a value. This lets us think about our services in a bit of a different way. So our service architecture can become much flatter. We can have a service that's responsible for pairing, finding just two people to play together, one for actually playing the games, but it doesn't know about games that are finished. Then have a service that's just responsible for the games that are being analysed at the moment. To get a better understanding of that, I'll look at the pairing service to start with. Pairing could be thought of as negotiating a shared identifier in this model. We don't actually have to go and update our game state. We don't have to say, I'm waiting for a pair and now I've found a pair. The pairing service doesn't actually have to tell anyone anything. So a way to think about it is to say, well, if I want to play a game and you want to play a game, all we both need to know is that we know the same game ID. So the pairing service becomes a lot simpler. It doesn't have to have a huge database. It only has to know about the 100 or so people that are currently looking for a game. It doesn't have to know about the people that used to look for a game. They can just go, well, I'm looking for a game, you're looking for a game, I'm going to give them the same game ID. Gets a little bit more complicated in that I want to play against people who are about my level and who want to play a game for about the same duration as me. So we might end up with a service call that looks something like this, where we have a bunch of constraints about the type of game I want to play. I want to play a 5-minute game. I want you to be about 1,500 in rating, and I don't want to wait longer than 30 seconds. And then when you've found a pair for me, call my URL and say, I found a game and here's your game ID. And that's all the pairing service needs to worry about. It doesn't have to go and tell the game service that I've found a pair and update the state and remember all of those things. It can just tell me what my game ID is and then forget that it ever told me anything. Internally, this pairing service is going to maintain an index list of waiting parties. It can be a very small database. It's only ever going to have maybe 1,000 rows at a time. Then you can get rid of them. Makes it very easy to scale. I can have lots of these services. It's not going to cost me very much to run. It's going to use that current list of players who are waiting, going to find the pair and send the unique identifiers. So is this pairing service independent? In our probability example, if one of these pairing services broke, or how would it affect the other services? So a way to answer that question is my service independent? Is to look at from four different angles. What does the service know? Well, the pairing service knows only about players waiting for a game. It seems like a reasonable thing for the pairing service to know. What is it told? It's told when a new player wants to pair. What does it ask for? It actually doesn't have to ask for anything. It doesn't have to go and ask for who's waiting for a game. It doesn't have to go and ask for a game state. And that's really important. And what does it say? Well, it just gives players the unique game ID. If I wrote this out and I was telling it about, and it was saying, well, I had to go and update the game state in this service, or I had to go and ask about what this player's name was or what this player's rating was, it would be a lot different. That would tell me that I had a lot of coupling, a lot of dependence. So if you go and have a service and you ask these 4 questions, it'd be interesting to see what you write down. For me, the important one there is that third line. What does a service ask for? A service shouldn't have to go and ask for the state of something very much. That's a sign of very heavy coupling, very high risk component. So how does the pairing service rate to the play service? They don't even have to talk to each other. Once I've got my game ID, I can go to the play service and say, well, I'm playing game 1, 2, 3. The playing service is responsible for just the in-flight games. This is a really important and understated aspect, is that I have helped companies in a lot of situations where they have very large databases that are catching fire all the time. And the reason for that is that they have something that needs to be fast. So for example, playing a game. When I'm playing chess, it matters that the system is very responsive. So the database has to be very reactive. The queries have to come back instantaneously. However, they've stored the history of everything in there. So the playing service, for example, would know about every game that's ever been played. So in a couple of years' time, it's got tens of millions of rows in it for every game of chess that's ever been played on my site. This doesn't make a lot of sense. We want the playing service to have a narrow scope. So we want to really narrow the scope of our services. By only having the playing service worried about games that are currently in flight, I've fixed my scaling issues. I've improved my independence. I'll just go back to this point again, that there's no direct relationship with the pairing service. If the pairing service went down and crashed, the game, and I'm playing a game right now, I don't care. Yep, nobody could start a game for a little bit, but that would be enough. So how does this relate to the history service? It comes back to our games being values. So once we've finished playing a game, we don't even need to store that game anymore. We would just pass the game as a value to the history service and say, here is the game I played, that's the result. The history service would store that. Its database would have a lot more rows. It would have the 10 million rows, but it doesn't need to be as fast to respond. It doesn't have that real-time constraint, right? So I've made the history server simpler by having it not need to respond as fast. It will have more data, but I've reduced the constraints on it. So that can just be a fairly static game. It might have the search, which might require a bit of memory. I can scale that independently of the other components. And then the history service gives out games as values. So if I go and ask the history service for a game that I've played or search, then it doesn't give me a reference like a game ID that I have to go and look up later on. It actually gives me the value of the game. So I could go and pass it to something else, like the analysis server or the analysis service. So analysis service is going to look at my game and tell me where I made mistakes. The analysis service just takes a game as a value. It's really important that it doesn't take a reference to the history server and then have to go and ask the history server for what the game was. It wants to just take a value. That opens up lots of opportunities. Maybe I want to analyze a game that I played in real life rather than on the site. Again, I could just write down the notation and pass it to my server, creating a bit of versatility, but also removing the dependence between services. The analysis service only knows about the state required for configuring games. So back to those questions. What does the service know? Well, it knows about how to analyze games. That makes sense. What does it have to ask for? It doesn't have to ask for anything. It knows how to analyze games. What does it get told? It gets told the game as a value. What does it tell us? Well, it gives us our analysis results back. Again, not a lot of mentions of other services in that story. So the key takeaways here should be that we should be thinking about independent responsibilities over shared nouns. We want to play games. We want to pair people. We don't want to have a game service that we're continually updating at every request that has to know about every game in every different state. It's just a slightly different way to think about building software. It's not the only way, but it's definitely a way that can have profound impacts on how you construct systems. So another way to think about, or another aspect of reliability, is how we actually operate our systems. How do they run? So if we look at our chess system, the first thing is we look at the services. What does it mean for the engine service to be failing? When we're talking about operational aspects, it changes the dimensions of what we're thinking about. When we're thinking architecturally, there's an engine service, there's one of them. But operationally, we're probably deploying 5 or 6 or 10. So now we have to think about the complexities of interactions of services with themselves. We have to understand what it means for that service to be failing. Is every one of these services failing? Is it just one specific service? There are lots of ways that we can do this, and different people are going to have different tools at their disposal, but simple ways can be very effective. So simple things like having a status URL, having services be able to say, well, I'm okay, or I'm not okay, being able to go and ask a service what to do. Once we've identified what is failing, we need mechanisms to route around that failure, to be able to deal with it. If we know something's failing, it isn't that great if that just wakes me up and I have to go and type and work stuff out. I want to be able to automatically route around that failure. Otherwise, what's going to happen is that, well, my engine's failing and I know about that, but, well, my chess service depends on that for all calls, so it's going to actually send more calls to my engine, which is going to make more engines failure, and eventually a cascade and everything's on fire and I don't actually know what the problem is. What we actually want to be able to do is say, well, this instance isn't working very well, it's responding slowly, so let's just take it out. We're just not going to send it any more traffic. So how we do that, we look at our health checks. Before making requests or periodically we can say, well, are all of our services healthy? If one of them can't be responded to or it's taking too long to respond, we can not route any traffic there. One of the things to watch out when you're doing this though is for entangled health checks. So when I've seen people go and embrace this for the first time, one of the first mistakes is always, well, I've got health checks and my health check is to go and test all of my dependencies. So an example is that our chest service depends on the engine. So in its health check, it goes, am I healthy? And it goes, well, engine, are you healthy? And the engine goes, no. But for the most part, the chest side's going to keep working. But instead of keeping on working, it just goes, oh, the engine's not working, so I'm not working. And then my automation tools shut everything down. Whoops. So we have to watch out for health checks. Health checks need to be independent, just like our services. So monitoring can be very effective, so simple things like health checks, but not all failure is clean. This is the 8 fallacies of distributed computing, which is basically a bunch of ways in which we make assumptions that come back and bite us. But one of the most important takeaways from this is the idea that a failure may not be a failure. A failure might be, well, I just never get a response, or the response is going to take 3 days to get back to me. And that can often be worse than a failure. If you give me back an error and say, oh, I haven't given you an answer, I can do something with that. But if you go away and then I'm waiting for an answer and I'm waiting for an answer and I'm waiting for an answer and more traffic's backing up, things can get out of hand very quickly. We want to get in this mode of this idea of serving some traffic is better than serving none. And there are lots of different ways which we can do that. The first public service announcement is that timeouts save lives. If we are dealing with slow networks or slow disk operations, we actually want to always have timeouts on these things. If you have to make a request to a third-party service, we actually want to fail if it takes more than a second or it takes more than what is a reasonable amount of time for that call. That lets us deal with those failures and maybe back traffic off so that we can recover or stop sending requests to that service because it isn't working. But we don't want to just sit there waiting forever. Once we've failed, we want to be able to retry. There are lots of different ways to retry, but just retrying as fast as we can, because we can, is normally not the best. So we want to retry with care and patience. So the plots on the left are some examples of some Amazon research for doing optimistic concurrency, but it's basically this idea of retrying is you try, if it fails, at what rate should you retry? So the idea of things actually getting a lot slower, so the pink line, we can't actually scale very well. However, if we add some randomness and some back off, so if I don't work, then I'll wait a little bit longer, and if it still don't work, then wait even more. Then we can actually get a lot faster by just actually slowing down. You also want to know your limits. So if you know that your database is going to fall over if it's getting more than 100 requests a second, there's no point in sending 1,000 requests to it. If every web request is going to generate 3 calls to the database and you can only handle 100 database requests, maybe you should only be accepting 30 web requests. So we want to taper limits and understand where we fail. Finally, if all of these mitigations failure and the engine service is totally offline and there's nothing we can do, then we still have to work out how to deal with this. We don't want the chest service to go offline just because our engine failed. So there are many patterns for this. The most common one is the idea of a circuit breaker. The actual details of this pattern aren't that important, but the important thing is that it means that you have to start involving your clients, whether they're API clients or users, in this idea of failure. So if the chess engines are offline, what do we do? Well, it might come back to actually having to change the UI. So this is what the UI normally looks like. I can play against a computer or I can play against a human. Well, if the engine's offline, playing against a computer doesn't actually make any sense. I can't actually do that. So actually being able to say, well, this button isn't going to appear if my engine service is offline. That's really important. So being able to incorporate users into this mode of failure is actually a great way to be able to regain independence. So we really want to understand what the failure is. We want to be able to route around it where possible and work within our capacities. In doing so, we'll be able to serve some requests, right, or most requests. And if we have to fail some, we have to fail some. That's not great, but we can. And then for those ones we can't service, in graceful degradation, it's better off letting them play chess but not letting them play against a computer, for an example. Okay, so we've built a system that's reliable, we can operate it, we're deploying things safely. Got to think about how we change systems. So this is one that affects very small products as well as very large ones. But I think it's small products or small teams that often ignore this one because, oh, well, we have a small problem, we don't actually have to worry about it, or we only have a single service. But changing system actually introduces a lot of dependence, but not obvious dependence. So I'm going to show a few examples of that. So it doesn't matter whether we've got little services or the monolithic for this example. But this idea of deploying new versions over time creates a weird dependence. So if we have one version, then we're probably going to have to make a change and deploy another version, and then another version, and another version. There actually isn't one version of our service. There are hundreds, infinity, over time. So for our pairing service, we don't just have one. We actually have lots of services at a version. That version normally has some sort of data storage. It probably needs a database to store its list of pairing partners. So when we deploy a new version, we get coupling between versions. The old version is written data to the database. The new version has to be able to read it. So even in one service, we have coupling and independence such that change has introduced a very large reliability risk into our system. It also affects the interface. The chess service needs to call a pairing service. If version n doesn't behave exactly the same as version n+1, something is going to break. We kind of create these black or white problems where we've got version A and it does X, and we've got version B and it does Y. We have to hope that they're the same. This is a type of dependence that is actually really hard to break, but there are a bunch of techniques that we can use. So if we have one service, and we want to jump to a new one, a different way to think about it is, well, we have one service, we actually want to have both services at the same time. We actually want to be able to run version A and version B in production together so we can make a better informed decision about whether it's going to work. It isn't a matter of putting version A in and then rolling back if it goes wrong. We actually want to run them both at the same time. So then we can decide, well, it looks like the new version's working. We'll send more traffic. Then we'll just turn off the old one, right? But there's these overlapping time periods that makes it less jarring. Or if things don't go well and the new service doesn't work, then we can roll back, or not have to roll back. We can just redirect traffic to the other service. So there are a couple of specific techniques that we use to achieve this. The first one is in-production testing or in-production verification. How this works is that if we have two service versions, we actually want to create a situation where we deploy a new version, but it's not actually giving any answers to our customers. All it's doing is saying, well, let me answer some questions or pretend to answer some questions, but don't actually send the results back. I just want to use them for cross-referencing. So how that works is we have a load balancer. We have two versions of our service. A request comes in. That request actually gets forked and sent to both versions. We get our results from both versions. They come back to the load balancer. The load balancer looks at them and goes, hey, they're the same. That's great. And just says, that's a tick. And eventually, after we've built up enough confidence, we can say, well, version n+1, that's working. We'll just switch to that. Or if it's not, then we say, oh, something's wrong. The implementation's changed. Something's changed, and we can go back to the other version. Another tool at our disposal is incremental deployment. This is similar but slightly different. This is where both versions are responding with real results, but we're mitigating the risk by only returning a very small number of transactions. So in this case, we have a load balancer. When a request comes in, we send most of our traffic to the old version, say 95%. The new version just gets a sliver, just 5% to start with. We need to understand success. Maybe it's simple, like a status code. Yep, 200 okay, must be okay. Or 500, that's probably bad. Or it could be, we're actually inspecting the results. Are the structures the same? Is it responding quickly enough? There are a whole bunch of dimensions for what working can mean. Once we've got to that stage, well, we can say, well, 5% of the traffic's working, let's send 50%. Still working, 95%. Still working, then we can turn off the old one. Or if things don't work, we can go back and, well, we can switch back to 100% of traffic going to the old one. But it is really important that we have both versions in production. We're able to make these finer grained decisions rather than create cliffs where we're either right or wrong, and something's either going to all break or not break at all. The litmus test for me for this is when I ask, could you ship a bad line of code to production and your system not go down? Not sure what that bad line is, but I don't know. Maybe it's calculation error, or it's something subtle like you start throwing an exception. I would like to be in a situation where if something gets through all of the tests and it gets deployed, that the worst thing that can happen is that maybe 1 or 2 customers get affected, but it isn't going to bring my whole site down. And that's really important. I've talked a lot about the deployment of code, but this gets, all of the things I've talked about are doubly important for things like data. So we have to share data over time. Data lasts a lot longer than code. It also applies to things like infrastructure. So machines or clusters. Basically, anytime we talk about having one of something, we only have one database and all of the versions have to depend on it. Or we only have one cluster. A common one that keeps coming up at the moment is lots of people are switching to Kubernetes. But they only have one Kubernetes cluster. So this is great. Kubernetes lets them do a lot of the other things I've talked about, like deploying multiple versions of their code. But then somebody goes, oh, we need to upgrade Kubernetes. And all of a sudden they're in trouble because they have to have the old version of Kubernetes and the new version of the Kubernetes, and they switch over and then it catches on fire and everything breaks. We need to be able to run such that we can have 2 Kubernetes versions running in production at the same time. There are lots of different changes on Kubernetes that can't be done in place, like adding security layers like mutual TLS. Okay, so we've got a long way into building this system, but I don't think it's very realistic. Nobody has asked us to do anything impossible yet. So, what happens when somebody does? This idea of being forced to use something that you know is going to break. I'm sure you've been in the situation where somebody said you have to use this service or you have to talk to this API, this other company, and it's not reliable. It breaks all the time. Doesn't matter how good our code is. We're always going to be dependent on this other thing. So I want to embrace this idea of trying to construct reliable systems from parts that aren't reliable. So the following is based on a true story. Names have been changed to protect the innocent. The real example is a machine learning example that I've faced in a company that I worked at, and it was extremely painful. The numbers are fairly realistic, but I've changed it to the test example to kind of fit with the theme and really protect the innocent. So in the chess world, things have changed dramatically over the last year. There have been chess engines that have been stronger than humans for the last 20 years. But they're based on brute force, the fact that the computers can move faster than humans. Basically, they try every move and work out what the best move is. Super interesting. But over the last year, AlphaZero, which is a Google project, which is applying AI neural nets to the learning games like chess. And AlphaZero just beat Stockfish, which is the strongest computer engine. It played 100 games, and it won 28 of them and drew the other games. This is pretty revolutionary. It means that we have a different way to learn from chess, and it's interesting for a couple of reasons. One of the ones that's interesting to me is the fact that the AI engines play moves that a human is more likely to make. I don't have to calculate 16 things in a row. It's using more intuition-based moves and getting good results. So as happens, as programmers, on a weekend, we go, oh, that's interesting. Let's try to copy the Google project. I've never written Python before. Let's write it in Python. Yep, I don't understand these algorithms. I'm going to write it anyway. I'm just doing this for fun, so I'm not going to write any tests. Yeah, it doesn't really work. It crashes all the time. That's okay. I'm just doing it for fun. Can you put it in production? No. Well, yeah, we're going to put it in production tomorrow. Sure, this is a story that has unfolded before. So what happens when you cross that line and you choose to ship unreliable code? So the particular example that I have was a machine learning example. It was to do with predicting of time series data. And at a guess, I would say, whilst I was talking, it would have an 8 in 10 chance of failing. It's not really good, pretty catastrophic. In fact, if it worked, I would have been very surprised. Basically, it followed none of the rules that I've talked about so far. It had a database that was embedded in it. Not only did it crash 8 in 10 times, that when it crashed, it corrupted the database, and it had to forget everything that it learned and had to start again, and that took an hour, and it was pretty horrible. So what do we do? What is a technique for dealing with something that is so inherently unreliable? So the approach that we took was, first of all, to try to take control of the interactions. So we wrapped up this library and created a proxy. And so what this proxy did is that every request that came in, we stored it off in a reliable log. So we had a journal of every request that had ever been made. And that started to give us options. We could use traditional reliable storage mechanisms for this log. And so when the service failed and inevitably corrupted its data store, basically we could just discard the service, but then use the journal of all of the calls that have been made so far to rebuild the state. So we'd kind of make the call again and make the call again and make the call again, so we didn't forget everything that we knew. So that gave us a reliable component. It was a bit slow and a bit clunky, but it worked, and we didn't have to deal with corruption of data stores anymore. Then, because our component was independent, we then could start applying redundancy. We could add another service, which got us back to 64%. Add 10, and we're at 10%. Add 20, and we're 1% chance of failure. So by taking control of the situation and building a service that was independent, that didn't start as independent, we were then able to use our simpler techniques, like just throwing more computers at it to get reliability. So this was a bit of an out-of-the-box example, but these are the types of things that we can do to build reliable systems from unreliable code. So the final thought for me is that reliable systems should be comfortable. We don't want them just to work all the time. We also don't want to be stressed about them. We don't want to be stressed about a bad line of code bringing down production. We don't want to be stressed about customers sending a bit of extra traffic there and everything breaking. I want to be able to go home, sleep well at night. So using a bunch of these techniques, we can get that. Things that we should remember from this is we can avoid failure by using more reliable parts. So don't do what I did. Or we could, if in failing that, we'd be resilient to failure by controlling the scope and consequences. So wrapping up things, making sure that one failure doesn't impact other systems. Service redundancy means we are going to get more failures. So if you have more services or more systems that you depend on, more things will break. That doesn't have to be a bad thing though, it gives us more opportunities to deal with them. Service architecture provides the opportunity to control the interactions and basically control the scope of a failure. Service granularity lets us trade the likelihood of a failure against the consequences of those failure. So we want to minimize the consequences. So that's back to the plane example. If we could say that we would always choose 4 engines if we knew that the only thing that could go wrong is the engine could stop working. Basically, we want to leverage all of these opportunities to create a system that works all the time. We can sleep well, and we can come to conferences like this and enjoy ourselves and not have to worry. So I hope everyone took something away. Some of these some of these techniques might be old hat, some of them might be new to you, some of them might be, I can't apply them to my system, but hopefully just a different way of thinking about systems and thinking about design and thinking about reliability will give you a few ideas to take away. So thank you.